This is Calculus 12, Chapter 5.1. Now we're going to be learning something other than differentiation. We're going to be looking at estimating the area under the curve. So if we have a velocity time graph, we can calculate the distance traveled by calculating the area under the curve. We want to calculate distance traveled between 0 and 4 seconds. So here we have velocity, here we have time. The velocity is 3 meters per second, and we're going to do this for 4 seconds. The area is 3 times 4, and that's 12 meters. If we do d equals vt, again, we have 3 times 4, and it's 12 meters. Let's look at a different velocity time graph. This one has constant acceleration. The constant acceleration is 1 meter per second, and we can see that that's a slope. And the area, we have the area of this triangle, and the area is 1/2 base times height, and that's 8 meters. If we look at our physics formulas, we have d is equal to 1/2 at squared. We have 1/2 times 1 times t squared. And again, we get 8 meters. This is not a proof that the area is the distance traveled. However, it's evidence of these two cases working. Now, what happens if the velocity is a curve? We can estimate it using finite sums. Here we have a velocity curve that is 1/4 t squared plus 2. You might recognize this as a parabola. So we have a parabola. We can perform an overestimate, and this is the right rectangular. Approximation method. So we can break these up into partitions, and for our purposes, we're just going to use one partition. So we're given 2 points. We use the right point as the partition. So we get a rectangle from this, and it's an overestimate. And this is just 4 times 6, so it's 24 meters. We can use the left rectangular approximation method. So we use the left endpoint. And if we look at the area under, this is going to be smaller. It's an underestimate. So 4 times 2, that's 8 meters. Or we can use something between. So we'll use the middle value, and that would be 4 times 3. That's 12 meters. And RAM just says rectangular approximation method. Now this is going to be confusing because you haven't seen this before. So the left rectangular approximation method is going from 1 to n being the number of partitions. This is a formal way of saying it, but basically we're taking the left endpoint, and we're going to use the left endpoint multiplied by the width of the partition and add them all up to get an approximation. So if we had 2 partitions, then our left would be this partition and then this partition. If we were doing the right one, we'd be taking this partition and then this partition. It's still an overestimate. And if we were to do a mid partition, we would take the middle of this partition and the middle of this partition and then add them up. So this is just a formal way of saying get that mid value and multiplied by the width. Here we're getting the right value and multiplying by the width. And the width is simply b minus a, so this is our a, this is our b, and divided by the number of partitions. Now, we don't want to normally do this by hand because it's a lot of work, so we can program our calculator to do this. Please watch a separate video on how to do this. All we have to do is enter our function, which is this one, and then we run the program. We tell how many partitions. We go from our A to our B. It'll give us our left, middle, and right approximations. And that should match what we did up here, 8, 12, and 24. And I'm going to demonstrate this example with the Casio. We have 0.25 x squared plus 2. Okay, now I'm going to execute the program. One partition, 0 and 4. And we see that we get our left, middle, and right approximations. If you're not getting this, you need to check your program or check your function. Let's look at another example. We're just going to do x squared with different partitions. Okay, we're going to start off with 4 partitions, 4, 0, 4. And we get 14, 21, and 30. That matches this. Let's do it with 8 partitions. We get 17 and a half, 21 and a half, 21 and a quarter, sorry, and 25 and a half. Running it with 16 partitions. 19,375. 21,3125. 23,375. And finally, we're going to run it with 32 partitions. Okay, we can see that these numbers are getting bigger, these numbers are getting bigger, these numbers are getting smaller. We're converging to a single value. These numbers are far apart, these numbers are closer together. We can actually get our calculator to do an exact answer. Menu 5, I'm going to graph this, change the window, 0 to 4. And for y, we have 0 to 20. And I can do gsolve. And what we're doing is we're doing this integral calculation. And I enter the bounds, 0 to 4. And we find that the answer is 21.3 repeat. Okay, and you can see these numbers are getting closer to 21.3, and you can get the actual answer if you make n large enough. We can do the same calculation on the TI. I already have x squared. The window's already set. Okay, now I'm going to calc, and what you want to use is this function, number 7. And again, we just enter our lower limit, our upper limit, and it calculates the area under the curve for us. It's actually called the integral here. Okay, and if we look at the rectangular approximations, we can see that, well, it's not here, but our left one starts here and goes here, here, and here. So these are the rectangles being generated for the left one. The green, don't have it here because it's too small. Green, 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 so those are green rectangles, and then the right are the blue rectangles. Again, that's what this formula is for, and these are the programming steps on your calculator. Okay, let's look at one more example. Okay, it's -1 divided by 2, bracket x minus 2, bracket squared, plus 5. Okay, so that's your times in here. Okay, that looks like a parabola. And we need to change the window. We have to go from 0 to 5. And this is going to be 0 to 20, I guess. Okay, G-solve. We want to always do a G-solve first, just to see what the actual answer is. Actual 19.16 repeat before we do our rectangular approximations. Okay, so exit menu, program, RAM, 8 partitions, left end 0, right end 5, and we get 19.785, 156, 19.248, 047, 18.222, 656. And now let's run it again with 64 partitions. 0 and 5 again. 19.26, 1779, or that's 80. 19.167938, and 19.066467. 467. Okay, you can see that all these numbers are farther away, and we're getting closer as we make n larger. And finally, we're going to run this with 512. And you can see it's taking slightly longer to calculate these. Doesn't converge very quickly. We have to get fairly large numbers to get fairly accurate, but you can see that In general, our middle rectangular approximation is going to be more accurate than left or right. Okay, one other concept we have to be able to do, area under the curve with tables. And recall these formulas. The middle one doesn't apply. It's slightly different. So let's look at the problem. We have a table. To do the left one, we do sum up all of these and multiply by the width, which is 10. This is our width. So you do all this, and we get something like 10 times 349. So this gives us 3490 feet. Now, if we're doing the right one, we skip the first one and take all the rest. Okay? However, we've already added up all these numbers, so we can just use our LRAM and take the width times the last element minus the first element. So this is 3490 plus 10 times 35 minus 0. And this gives us 3840. And to get MRAM, all we have to do is average the left one and the right one. So LRAM plus RRAM divided by 2, and that gives us 3665 feet. Okay, so doing this by hand will likely give you an error. So what we'd like to do is have another program, RamList. You can change it to list if you like, or you can just leave it as RamL. So what you need to do is type in this program. You just enter these numbers. Okay, that's your table. Just ignore this. This is just extra data from another problem I was working on. So to see this example, I would go to stat function, and then I enter my list. 0, 44, 15, 35, 30, 44, 35, 15, 22, 35, 44, 30, 35. You can see with this list, it's very easy to go back and check your values to make sure they match your table, so that reduces the number of errors. Now I can go to the program, run RamL, tell the program what the width is, and the width is 10 for this one, and we get our values that match our calculations. So if you need the video for how to enter these programs, please proceed to those. But that completes this lesson.